You want to sound test here?
Test. Is that good? Can you hear me? Fred?
Okay, we're gonna go ahead and get started. Thank you all so much for your patience. We were all surprised by that final exam. I personally feel very glad I was not one of the students taking the exam and instead just had to wait outside. We're so excited to see you all today and so many of you. We have perfect weather. It is chilly, but it is super clear, so we should be able to see some really cool things. I'm your host. My name is Amanda. I'm a lecturer in the department and also the outreach coordinator. We'll get started with some trivia. We'll go a little fast through trivia and announcements so that we don't get too far behind schedule. We'll start with trivia, so our telescope trivia. The way this works is we'll have 5 questions. Collaboration. Okay, we're gonna change our connections real quick. We really encourage collaboration. Science doesn't happen without it. All right, we're back. Trivia for real this time. All right, our first question is, which of these are not real telescopes? Oh no, Jen. The background changed. Okay, maybe we're gonna get.
All right, we're skipping trivia.
Oh, trivia is fun though.
Okay, we can fix this very fast.
Okay. Make the text one. Oh. Okay, we'll skip this one though.
All right, you already know the answer, so that's cheating. Just call it.
Yeah. Fred and I both were on it.
Oh, that's fine.
No. Fred was on it. All right. Woo! Good thing we were not the ones taking the final exam today, because it would not have gone well, it seems. Okay, our question is, the largest telescope in the world is currently the Gran Telescopo Canarias in the Canary Islands by Spain. How big is it? So here are your choices. Chat with folks around you, and in a moment, I'll ask for ideas. You'll show me 1 for A, 2 for B, 3 for C, 4 for D, and 5 for E. Okay, let's vote. 3, 2, 1. Show me your thoughts. I see some 4s, I see 1s, I see 5s. I see a 3. I see a 2. I think we have all of the possibilities. Telescope on Earth is just over 10 meters, but we're always looking to make bigger ones. So our next question, there are plans to make a telescope even bigger. What will its name be? All right, let's see your votes in 3, 2, 1. Okay, I see 1s, 2s, 4s, a 5, and a 3. All right, so you might think this is a joke question, but it's not. Astronomers are very bad at naming things. It's either extremely obvious or a number. And this is the extremely large telescope. That is its official name, or the ELT, because that's much too long for any of us to say. Okay, our next question. Why do some telescopes need to be in space? All right, let's see your thoughts. Our instrumentation expert in the room was saying 5 because it's cool. All right. I'm seeing a lot of 4s, and that is correct. So the Earth's atmosphere blocks a lot of kind of light. That's why when we go outside, we have to wear sunscreen, but not a lead vest to protect us from the X-rays that are in space and coming from other sources. All right, our last question. Which of these have we managed to observe with telescopes? All right, let's see your answers. All right, people have caught on that we're tricking you with this one. So good thing for those students, we weren't the ones who wrote the final. So it's everything except for exomoons. So we can see galaxies, we can see stars, we can see the earliest light from the universe, we can see exoplanets that are planets outside of our own solar system, and we know they must have moons going around them, but we haven't observed one yet. But there are some graduate students in the department who are working on that. All right, our announcements. Our mailing list is the best way to find out about our events. This is the last event of 2025. We will have more talks in the spring. We won't have one in January. We need to officially book the rooms, which we can't do yet. So our schedule is TBD, but we're looking at the beginning of February. We'll send out an announcement 2 weeks before. All right, there has been much further ado, but without any more, I'll give it over to our wonderful speaker. She's a graduate student in the department. She doesn't know, but I'm going to sabotage her so she can't ever leave and graduate. But please give it up to Jen Mead.
Hi, everyone. Thank you very much for coming tonight. And again, very sorry for the delay, but trust me, a lecture on astronomy is way more fun than taking an exam. And I'm sure we're all glad none of us are in that position. So telescopes are collections of mirrors and lenses that astronomers have been using for centuries to shatter the darkness of the cosmos. Now, many astronomers who are theorists or who are computational astronomers will tell you that their chosen pen and paper or their chosen computer is the bread and butter of their science. But telescopes are the bread and butter of all of astronomy. And the reason that is because without telescopes, we can't see anything in the cosmos. Yeah, you can look up at the stars, right? You can see some of the stars at night, but all of those stars are in our backyard. They're not very far away. They are in the Milky Way. If you go to the southern hemisphere and it's a nice and dark night, maybe you can see a couple of galaxies that sit just outside our Milky Way, but that's about it. You're not going to see any of those exoplanets. You're not going to be able to look for those exomoons, and you're certainly not going to know that our galaxy is made up of billions and billions of galaxies. Or sorry, not our galaxy, our universe is made up of billions and billions of galaxies, but our galaxy is made up of billions and billions of stars. And so you're all here, right? This audience is a little bit self-selecting in that you are already interested in astronomy. And so many of you probably know what a telescope does. In fact, many of you have probably looked through a telescope. In fact, many of you have probably looked through a telescope with us on one of our observing nights. But I want to ask a member of the audience, can somebody tell me what a telescope does for us? Yeah. It does help us see stars. What else does it help us see? Yeah. Mm-hmm. Yes. Yeah, so we have telescopes that you can use from home. Some of you may have those. They're fairly small. They're kind of similar to the ones that those of you who have joined us for our public observing nights that you've seen us use. But there, like you said, there's also telescopes in space. And the key thing that you said was that it helps us see things that are far away. So it helps to bring those very tiny things closer. And in the words of the person who invented the first telescope, Hans Lippershey, the telescope, or it was actually a spyglass that he invented, is for seeing things far away as if they were nearby. And so the telescope, the first telescope, was invented in 1608. It was originally a spyglass that was intended to be used on ships to help sailors navigate in the ocean. However, just a year later, Galileo Galilei conscripted that telescope in order to see things in outer space. And so Galileo used that very successfully to make a lot of core discoveries that actually just changed the way that we think about astronomy. But it wasn't until 60 years later that Isaac Newton then changed the design of the telescope, which I'll get into in a little bit, to make it into the type of design that we use in our telescopes today. And so that brings us all the way from the 1600s to the present day. That's about 300 years of, well, some evolution in telescope design. But effectively, right, we're using the same tricks with mirrors and lenses that they used back in the 1600s. And so I want to highlight some of the things that these people discovered with these telescopes so early on. And so Galileo, I think this is a good sign for all of us in the room. He was a university student who actually just dropped out of university. And so it kind of says that you can still be brilliant, right? As one of the greatest scientists that we think of today, right? You can still be brilliant and not have gone to university, right? So good for some of us in the room. Galileo is responsible for perfecting what we call the refracting telescope. And I'll get into the differences in a little bit, but keep that word in mind, refracting. He used this telescope in order to look at a lot of things, including the moon, Saturn's rings, the moons of Jupiter, and I think this is just really cool. The moon is one of the biggest things in our sky. Well, actually, I think it is the biggest thing that we can very clearly see in our sky. But you can't really see all of those craters on the moon very well with just the naked eye. And with the telescope, Galileo was able to observe the moon, and you can see his drawing in that upper right corner is actually a very good reflection of those craters and the shadows that you see on the moon. The moons of Jupiter is another thing that Galileo observed. There are four biggest moons of Jupiter that he was able to observe. There are currently 95 acknowledged moons that we've seen with Jupiter. Can anyone name what the 4 moons that Galileo observed were? These are the Galilean moons. Yeah, go ahead. Ganymede, Callisto, Io, and Europa. Very good. So those are the 4 largest moons of Jupiter that he was able to see. And the reason that the observation of the moons of Jupiter was so important is because at the time, geocentrism, or the idea that everything revolves around the Earth, was the prevailing idea of our solar system at the time. And this was being pushed by the church. And to say otherwise was considered heresy. And so this observation of what Galileo referred to as stars, but are actually the moons of Jupiter, orbiting around Jupiter and not the Earth, was the first kind of evidence or definitive evidence that maybe not is all as it seems, right? Maybe the geocentric model is not correct. The other major observation that Galileo made was the phases of Venus. And so in the geocentric model, all of these planets and the sun orbit around the Earth. Now, we knew, even when we were believing in geocentrism, that Mercury and Venus must be interior to the sun because we always saw them next to the sun. And so we knew that they weren't beyond the sun. But Mars, Saturn, Jupiter, those were all beyond the sun. Now, the way that we were able to explain things like the retrograde motion of these planets across the sky was we used a geometry called epicycles. And so as these planets and as the sun goes around the Earth, they're also going in little circles around their orbit. Now, it's pretty complicated, but at the time, right, like maybe that makes sense, especially if you believe that the Earth is the center of the universe. But the problem is that with the geocentric model, if Venus is interior to the sun's orbit, and it's always in between the Earth and the sun, then when Venus passes between the Earth and the sun in its little epicycle, you will never see the full face of Venus illuminated. So you're only ever going to see the dark side of Venus or maybe a crescent moon. And so that's that left side of the right diagram. However, what Galileo actually observed was the full set of phases of Venus, just like you see the full set of phases for the moon. And what that really showed was that Venus has to be going around the sun because we can't see the fully illuminated face of Venus if it is always between us and the sun. And so this is a second piece of evidence that really kind of suggested that the heliocentric model was the correct model for our solar system and not the geocentric model. And this was all done using just a basic refracting telescope. Now, if we fast forward about 60 years, Isaac Newton, also an unremarkable university student, so I don't know, there seems to be a trend here. Maybe we should all stop getting PhDs, like seriously. But Isaac Newton, he later came up with the theories of calculus, of light, of gravity, some of these things that really tie together physics as we know it today. But what he discovered was that one of his famous experiments was shining light through a prism and discovering that when you shine light through a prism, it bends, right? Not only does it bends and separates the different colors of the rainbow. And this is actually problematic because the way that the refracting telescope is built is that it bends light through lenses, and we'll cover this in a second. But because it bends light through lenses, it bends all of the colors in different ways. And so this creates little rainbows. They're called chromatic aberrations, right? That make it a little bit problematic to view with what's called a refracting telescope. And so Isaac Newton improved on the design of the telescope by making a reflecting telescope. And so light can move in many different ways. As you know, light can be transmitted as it does through air. The lights on the ceiling here are transmitting down onto all of your lovely faces. But it can also refract. So remember that word refracting, that Galileo built that refracting telescope. Light bends when it encounters different materials, right? And lastly, light can reflect, so it can bounce off different surfaces, right? And you all have encountered your reflection in a mirror before. That is light bouncing from your face onto the mirror and then back into your eyes. So how do these two different telescopes work? So we have our refracting telescope. If we have light coming from a planet, a star, a galaxy, and it comes through our telescope, we have two lenses. The first takes that light and it bends it into the second lens, right? So it's focusing it just a little bit, making that light focus, bringing it together for your eyes to observe. But as you can see, those light rays, they're crossing, right? And so that's a little bit problematic because if that light had just gone straight, you would have an image that disperses. And so that second lens helps to bend it back and bring it in line with your eyes. And so as I said, this bending of light through lenses causes problems, right? Because it causes those chromatic aberrations because all those different wavelengths of light bend differently. Now I want to do a little demonstration. If I could have my volunteer kindly step up. And this is going to show you what happens when light bends differently. If you could just grab a piece of chalk. What I'm going to do is I have 3 different lasers of light. These lasers, I'm not going to point them at you, but you should never look a laser, point it in your eye. Do not do that. Each of these lasers is a single color of light. It's a single wavelength. Have here at the front is going to bend each of these different colors of light in different ways. And what we're going to see is that each of these different colors of light end up somewhere different on the chalkboard. So I have a red one, a green one, and a purple one. Who wants to take a guess which one ends up on top? Green, red, or purple? I hear red. What about other guesses? Just the highest, gets bent the least. Red? Okay. Which one is going to end up on the bottom then? Purple, logic, right? Rainbows. We know rainbows. Roy G. Biv and all that. All right. So you know I'm not cheating. I'm placing this laser on this flat surface here. I'm going to point it right through the laser now, like right through the prism. Now let's see, where's that line? All right, can you mark where that line is? Great, thank you. All right, now we're going to do this green laser here. Whoop, let's see if we could get a line across the board. If my hand can be a little bit steadier, could you mark it somewhere close to that line? Okay, our green line is, oh, surprise, surprise, lower. All right, and then we have our purple laser. Let's get it through the prism. Can you see it? Where is it? Down there. All right, so you guys know rainbows. Congrats, you made it through kindergarten. But as you can see, each of these different wavelengths of light were bent differently as it went through that material. Now, the next thing I want you to do, is it possible that we can get the lights off for a second? Now, you may or may not be able to see my phone flashlight, but hopefully most of you have phone flashlights. Other way. Piece of plastic. One of them. There we go. All right. Now, what I'm going to do is I'm going to turn on my phone flashlight, in theory. You can try this with your own flashlight. And what I want you to do is look through that diffraction grating at the flashlight. What do you see? A rainbow. Or stars. Yeah, you get a little bit of diffraction, especially if your eyesight's not so great. Red, green, purple, yellow, orange probably. Great. You'll see a lot of white light, but you're seeing a lot of rainbows too. So this is a very similar effect. Those diffraction gratings work in much the same way, that light gets bent differently as they pass through, in this case, extremely tiny slits in your diffraction grating. In those single sheets of diffraction grating that you have, there are thousands of tiny slits, right? And what's happening is those different wave fronts of light are getting bent in different ways as they encounter those slits. Okay, I'm going to turn this off if we could get the lights back. Okay. So Now you kind of have an idea of where those aberrations come from. They're not so great. You can imagine if you've got rainbows all over your images of your galaxies and stuff. Pretty, but honestly a little bit annoying. So reflecting telescopes are actually nice because light gets reflected in the same way. And so as light comes in, it bounces off what we call the primary mirror onto what we call a secondary mirror, and then it is bounced through one lens into your eye. That lens helps to focus that light so you don't get that blurry image. Now, this is just so if you've observed with us outside, you've seen those Dobsonian telescopes we have, the long tube telescopes that we observe through. This is exactly what those Dobsonian telescopes are. They are reflecting telescopes. They're actually Newtonian reflecting telescopes. If you have been upstairs in our observatory, which we just opened up last lecture, and we will be using again tonight, our telescope up there is a slightly different design of reflecting telescope known as the Cassegrain telescope. And it's a very similar concept where light comes in, it bounces off a primary mirror onto a secondary, but that light gets bounced directly back through a hole in the primary mirror right onto your eye or onto whatever instrument may be back there. Fun fact, your eyes are lenses too. So a lot of you know that you have lenses in your eye. And if your eye works perfectly, right, light from some object is going to go through the lens in your eye and it will be focused onto a single point on the back of your retina. But if you're like me and you have terrible eyesight, this is a diagram of what happens if you're nearsighted. The lens in your eye bends light a little bit too much, right? And so you can see the point where all those lines cross is in front of my retina. And by the time all of those different light rays from the different parts of that tree reach the back of my retina, it is no longer a focused image. And that is what makes it all blurry. So this is what glasses are for. Glasses for whatever your eyesight is, right? It will bend the light away so that when your eye lens bends that light is now focused on the back of your retina into one single point. And so all of this kind of seemingly simple telescope design, just these lenses and these mirrors, is what is still being used in the modern age of telescopes, but mostly the mirrors, because again, we talked about the problems with the lenses. Today, astronomers have more than 1,000 ground-based telescopes around the world. This includes a lot of the big science-producing telescopes that you may have heard of, like the Keck Observatory, ALMA, some of the ones that we'll go over today. But it also includes smaller observatories like the one that we have upstairs on our roof. We also have more than 30 active space-based telescopes. And the reason we have so many telescopes is because there's so many different kinds of light. And so in order to understand kind of, what we're seeing, right, we need to understand the electromagnetic spectrum. And so all of you, I can see all of you in different colors, right? And those different colors are what are known as the visible spectrum. And you can see from up here, that's a pretty small part of the electromagnetic spectrum. We, of course, have the UV rays that burn us when we are outside that come from the sun. They're the X-rays that you're exposed to when you break a bone and you go take an X-ray, because that was a very creative name. We have the infrared, that is what comes from the signals of your TV remote. Microwaves, guess what that's used in? Your microwave, good job. And you also have your radio, which if you are older than like 25, maybe you remember having a radio in your car. But if you're younger than 25, guess what? Your Bluetooth still uses radio. So you do know radio waves. But as we kind of briefly alluded to with the trivia questions, we can't just build everything on Earth, right? Some things do have to go to space. And it is exactly because some of those wavelengths cannot reach us on the ground. And so I want to take a quick detour. Actually, I already opened this. Maybe it reloaded. Okay, so we're going to wait. We're going to go to this National Astronomical Observatory of Japan. Gives a really cool tour of the different wavelengths of the universe, the kinds of things that we can see, and the different telescopes that we have. So I'm going to skip to the wavelength guide, where you can see a lot of, not all of the telescopes that we have, but a lot of the big telescopes that we have kind of laid out in this wavelength range, where you can see that we have certain observatories like Chandra that can see in the X-ray. We have the Hubble telescope, which mostly sees in the UV and the optical and some infrared. We have the James Webb Space Telescope, which I'm sure all of you have heard about in the news in the last few years, which observes mostly infrared light and so forth. Now, the reason that we need these different telescopes is not only because there's different kinds of light, but if I can, maybe I can't click on it. Well, that's slightly problematic. All right, well, long story short, different astronomical objects will emit in different wavelengths of light. And so things like the radio will allow you to see cold gas, whereas things like the X-ray will allow you to see highly energetic phenomenon like supernova. And so you're not going to be able to see everything that's going out in the universe with just a single wavelength of light. Okay. And so some of these wavelengths, like we said, they don't reach the ground. We actually only have the optical and the radio which reach the ground. And so if we want to know anything about what is going on in the X-ray, the ultraviolet, or the micro and the infrared, we need to go up and out into space. The other question that was brought up in our trivia is, why do telescopes keep getting bigger? Like, why didn't we just build one and get it over with, right? The reason that we keep needing to build bigger and bigger telescopes is, one, because the engineering wasn't there to build a big telescope, 20 years ago, right? It's actually quite a feat of engineering not to build a single monolithic mirror that is 30 meters. It is too heavy. It will sag. It will break. We don't want that. That's just a lot of money down the drain. And so those mirrors actually have to be broken up into segments, and the amount of engineering that goes into keeping those segments aligned, right, tilting them so that we're getting a perfect picture is really, really like a huge feat of engineering. But the reason that we need such a big telescope in the first place is because you can think of telescopes as these giant light buckets that collect rain, not rain, but photons, right? And things that are very, 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 very far away are only going to have a few photons that reach us, right? And so if you build a tiny telescope, you're only going to collect like one photon, right? That's not great. So if you build a much bigger telescope, you can collect many of those photons, even from things that are very far from Earth. Larger mirrors will also give us a better angular resolution, which means that we can separate things that are very far away from us, but are actually physically close together. So if you think about a car with its headlights on that's coming towards you in the dark, when it's very far away, you can't see those two different headlights apart, but when it gets closer, you can separate them, right? And that is what we call angular resolution, okay? All right, so that brings me to the interactive-ish portion of the talk where you guys get to guide a little bit what I'm going to talk about. I have 12 different telescopes here that I have kind of compiled some information on. They cross different wavelength ranges. They are ground-based, they are space-based, they are current, and they are future. They cover different topics in astronomy. And so what I want to solicit from you guys is kind of a list of either questions that you have about astronomy that we can maybe think about how telescopes are answering, or if you know some of these telescopes, hand raising. But I'll write down, let's take like 1 minute to write down and brainstorm a couple topics, and then we'll take a vote on what we want to hear about, okay? All right, let me chalk. All right, does anybody have, I'm putting myself on the spot here because this could potentially cover like a huge range of topics in astronomy. So I reserve the right to veto any I don't want to talk about. But you also have the right to suggest it. So hit me. Hubble? Okay, what about you? Adaptive optics, okay. AO, Hubble. What else? Yeah. You want to hear about future telescopes? Okay. Yeah, don't you go ahead. Yep. Yes. If you observe the same object, yeah. Reuben? Reuben's a good choice. Okay, I cannot write on the chalkboard. What else? Yes. Oh, I don't have information on that on there, but I can definitely talk about it. Yeah. James Webb. Yeah. Well, that seems popular. Yes. How do we build it? We don't. We don't. We built it here on Earth. Then we launch it, and it does its own thing in space. Yeah. Dark matter. Okay. I was afraid of that. Yes. Ooh, excellent question. One I don't have in my talk, but I would love to talk about. Hang on. Traffic. Yes. Okay. Habitable worlds. Yes. Exoplanets. We've not found an exomoon, so can't talk too much about that. All right, this is a good list. Anything else that we want to add? There's it's not like literally over Wi-Fi, but you just send a signal towards Earth and then we capture it. Yeah, so I don't know exactly what wavelength they use, but it's the same way that you would transfer data, yeah. Mm-hmm. Yes. Yeah, so you do have to worry about quality of the data, yeah. The picture of the black hole. Black hole, I can talk about that. I can talk about all of these, but all right, two more. Yes. No. They emit in different wavelengths of light, and so if you get more massive stars, they'll emit at closer to the UV end of the spectrum, and if you get smaller stars, they'll emit in the red end of the spectrum. Yes, in the back. Early universe light. Okay. Okay, we have a very long list here. I do not have time to go over it, although I wish I could. And if you still have questions after, you can come talk to me. All right, I can barely see it, so I'm sure you can't. Can we get votes for James Webb? Raise your hand if you want to hear about James Webb. Yeah, me too. Okay. Habitable worlds. Okay. Oh, hands came up later. Wait, do that again. Okay. Exoplanets. Oh, wow, really? Shocking. Okay. The black hole image. Okay. Early universe light. Okay, we'll kind of cover it with James Webb. So, adaptive optics. It's actually really cool, and we're gonna kind of do it when we talk about black holes, anyways. Hubble. Hubble has some cool images, guys. Okay. I'm gonna skip future telescopes because two of these are future telescopes, but Reuben also has cool images, guys. Okay. All right, well, I have some discretion over what we talk about. So I'm gonna talk about a couple things. I will start with James Webb since that had a ton of votes. So James Webb, I'm sure most of you have heard about it in the news, right? It's this, the latest great science, because I focus a lot on the early universe and thinking about how the first stars form. And so here I am talking to you about telescopes. I don't actually straight up use James Webb. I actually do mostly simulations and some observational stuff. But James Webb, super, super cool. James Webb, because of the wavelength that it observes in, which is the infrared, it is able to see through gas and dust, and is able to see what would have been optical and UV light all the way back in the early universe. Now, James Webb has a 6-meter mirror, which for a telescope in space is quite large. We don't need as large telescope mirrors in space as we do on the ground because the Earth's atmosphere is not in the way. the Earth's atmosphere is not screwing up our images. And I'll get into that a little bit when we talk about like the black hole or the identification of the black hole and adaptive optics and such. James Webb, super cool. Like I said, it's observing the first stars and galaxies that formed in our universe. It's also able to look at different sites of star formation because it is seeing in that infrared. Normally, when we look in the optical, we can't see through gas and dust, which is where stars are forming. But infrared light is able to get through dust, and so we were able to see sites of star formation. And James Webb is super cool because it can also look for biosignatures in planetary atmospheres, and that is one of the main drivers or science goals that James Webb has. Oh, and I should go back and say this image, this beautiful image here, is a comparison of the Hubble image, excuse me, of the Carina Nebula versus, which is on top, versus the James Webb image, which is on the bottom. You can see that James Webb has superior resolution to Hubble. You can also see, if you look carefully, that through that gas and dust, can't quite see with Hubble because Hubble is looking in the optical where that light is being absorbed and blocked by the dust. James Webb Space Telescope is named after James Webb, the man, who was the second NASA administrator. One of the reasons that we named the James Webb Space Telescope after him was because he was a huge champion of early space telescopes, and he helped to launch the Apollo program. And so he really helped to drive NASA into the space age of telescopes. Now, James Webb has been launched for nearly 4 years now. It launched on Christmas Day, which was like the best Christmas astronomers have had like ever, back in 2021. And since then, it's had a huge number of discoveries. It's discovered the furthest known galaxy to date. Before that, Hubble had that record. And it's also discovered the furthest single star, which was 13 billion years in the past. And we were actually able to discover that single star not because we can see the single star like as a point, but because it underwent something called strong gravitational lensing. And so its light was magnified like a lens would magnify light using like a giant cluster of galaxies that was in front of it. And so mass, maybe I shouldn't have gone down this rabbit hole with strong gravitational lensing. Mass can act as a lens, right? It bends space-time around it, and light has to follow the curvature of space-time. And so that's exactly what happens, is that light gets bent around that giant mass. It acts exactly like a lens, and that light gets magnified, which is how we found that single star. It's also discovered a series of little red dots. Don't ask me what they are. We are still debating that. We think that they are active black holes in the early universe, though. But this was really cool because this was something that was not predicted by astronomers. We didn't expect to find this, and then we found it all over the place in the early universe. But discoveries are ongoing, and there are literally like tens, if not hundreds, of papers using James Webb data every single month. Fun facts, the James Webb Space Telescope is very shiny. Its mirror is coated in gold, and it also has a tennis court-sized sun shield that helps to protect it from the sun's radiation. On one side of that sun shield, it is a balmy 80 degrees, but on the other side where the telescope is, we're at negative 370 degrees, so if you think it's cold outside today, no, it's not. Oh, well, we're not doing Chandra. So let's head back here to home. What was the other thing? Dark matter was also a big one. Let's see. Dark matter. What do we want to do with dark matter? Well, we could do, actually, no, I lied. We do want to do Chandra. Let's go to Chandra. Maybe, in theory. All right, let's go back to James Webb and then go to Chandra. So apparently that wasn't working. X-ray telescopes. You may wonder what X-ray has to do with dark matter. And it has to do with dark matter because we can actually see other things that are not dark matter. X-ray telescopes, though, are super, super cool. The design is not like the mirrors that I told you about in the past, all right? So we do not have a single reflecting mirror that captures light. Instead, we have a bunch of cylinders of mirrors that are all concentric to each other and stacked all the way down. And the reason that we need to do this is because X-rays are extremely powerful photons. And so if it was just to bounce off of a mirror surface, like optical light would, it would actually just go straight through. And that's pretty useless if you want to actually see those X-rays. And so what we actually need is for those X-rays to just graze the mirror. And if they just graze the mirror at the right angle, we can actually affect their path and focus them onto our telescope instruments. And so the reason I'm talking about Chandra, I'm going to skip forward a little bit because we are running a little bit low on time. The reason I'm talking about Chandra is because it was key in one of the major pieces of evidence for dark matter, which is the bullet cluster. And it's not that Chandra observed dark matter. We have not actually observed dark matter directly. Let's just get that straight. But what we have observed is the effects of dark matter. And so what you're seeing here is in pink, high energy X-rays that is being emitted by heated gas. So these two galaxy clusters, what is highlighted in blue on both ends, those are galaxy clusters that have passed by each other, right? Their gas, their regular matter, has gotten heated and shocked by slamming into each other. But we can actually see that most of the matter, those blue spots, has passed right through. So most of the mass is on the two ends of that image. And you can tell the mass is there because if you look very, very carefully, you see these streaks in the image, those arcs that are kind of going through along the sides of the cluster. That is the strong gravitational lensing I was telling you about. So you know that there's a lot of mass there and it's bending light. And let me tell you, see that you're getting that light bent, you know that most of the mass is there, but mostly energy from your baryons, your regular matter, your regular gas, is coming from the middle. And so we know that there must be something there that we cannot see, it's dark matter, that has passed right through. And so Chandra was actually quite critical in developing this, one of these major pieces of evidence for dark matter. Okay, should we do a Chandra fun fact? Let's see. Somehow we moved on. Oh, yes, Chandra fun fact. The mirrors of Chandra have to be so smooth because we are looking at high energy X-rays, right? There cannot be aberrations in the mirrors. It is smooth to within a few atoms. And so if Colorado, you know, that state with the Rockies, were as smooth as Chandra's mirrors, Pikes Peak would be 1 inch tall. Pretty small, right? If you've seen Pikes Peak. I have not actually, so maybe that's more impressive to those of you who have seen it. Okay. All right, let's say we do maybe 1 or 2 more. I'm going to do adaptive optics because we can talk a little bit about black holes on the way. And so I'm going to talk about the W.M. Keck Observatory. This is an observatory that is located on Mauna Kea in Hawaii. It is one of the largest telescopes that we currently have on Earth. It is a set of 2 twin 10-meter mirrors that observe in the infrared. Now, 10 meters, right, we're just slightly smaller than the largest current telescope on Earth. But Keck is particularly special because it helped to pioneer the technology for adaptive optics. And for those of you who don't know what adaptive optics are what allow us to get not blurry images thanks to our atmosphere. So our atmosphere is annoying. Yeah, we can breathe, but like as an astronomer, I really kind of hate it. What happens is that as light passes through the atmosphere, there are molecules up there that help you to breathe. There's a lot of water up there too. And as that light passes through the atmosphere, it interacts with those molecules and it gets scattered just a little bit. And as we know, scattering light, right, is going to make for a blurry image. And so what adaptive optics is that it takes essentially a laser and it creates a fake star on the sky. And that laser then bounces back to us, and we can measure how the wavefront, or how the light, is affected by the atmosphere. And so in real time, we can measure the changes that we're getting from the atmosphere, and we can apply those corrections to the images that we are taking. And of course, the atmosphere is always changing, right? And so it's critical that we keep that laser going. So don't fly it plain by Keck, okay? All right, so major discoveries. Keck was absolutely critical in the discovery of the black hole at the center of the Milky Way, which we lovingly call Sagittarius A star. And this discovery actually led to a Nobel Prize for UCLA astronomer Andrea Ghez. And the way that we discovered this black hole at the center of the Milky Way, well, one is thanks to adaptive optics. And so you can see, if we look at the center of the Milky Way, what happens if adaptive optics are off? Can't see much, right? Can't see into to distinguish all of those different stars from each other. Now this here is just a really cool video of how we identified the black hole, which is actually not by seeing the black hole directly, but measuring the motions of stars that go around the black hole. And so the galactic center is extremely crowded. And so you can imagine that having good angular resolution is necessary because all of those stars are very close together. And what Andrea and her team did was they tracked the motions and orbits of stars going around the black hole, or what they thought was the black hole, for several years, right? And so what you see traced out is some actual data and some projected orbits, right, which you can mathematically figure out. And you can see that there are, oh, let's start that one more time. You can see that there are a few stars that are very close to the center of the black hole that are going around very fast. And so by measuring how quickly those stars are going and the orbits that they have, you can tell how much mass must be in the center. And we know that the amount of mass that was in the center was way too much to like reasonably fit in the space that we can't see, right? And so that matter must be so dense, right, that its density means that it must be a black hole. All right. Do I have time to do one more? No? Okay, I don't have time to do one more, guys. Sorry. So if you want to know about it, you're going to have to come and chat with me. So I'm going to skip very quickly to the end here. You can build your own telescope. Warning, you should never, ever, 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 do not come after me. Look at the sun with your telescope, okay? You should never look at the sun, period. Definitely not with a telescope, unless it is specifically a solar telescope, specifically. However, if you are interested in building your own makeshift telescope, right, it's honestly probably only good for like looking across the room, but it's cool anyways. I have some instructions somewhere over here that you guys can pick up when you leave, right, on how to build your own telescope using just masking tape, a couple of lenses that you can get out of like reading glasses, and some toilet paper or paper towel tubes, okay? So grab one on your way out. And the last thing I want to highlight is some of the cool things that are in our night sky that you can see if you have your own telescope this December. Most immediately, although it is snowing tomorrow night, so that sucks, is the Gemini meteor shower. It is one of, in addition to the Perseids, one of the coolest meteor showers of the year. If it is not cloudy tomorrow night by some magic or Sunday night, I highly recommend going out and looking for it. Better if you can get to a dark spot. There's also a peak Orion Nebula viewing on the 15th, just a couple days from now. The latest interstellar comet to come through our system will make its closest pass to Earth on December 19th. There's the Ursid meteor shower close to Christmas. It is not as impressive as the Geminis, but still worth going out to see. And then right after Christmas, you can see Saturn and the moon together in the sky. And so that would be also very cool with a telescope. All right, with that, I am happy to take any of your questions. And thank you so much for coming out and waiting so long for this talk to start today. Thank you.
All right, Jen, can you advance to the question slide? So there are two ways to ask questions. You can raise your hands or you can type them if you go to this form. We won't get through all of them, but we'll do as many as we can.
What was the magnification on Galileo's telescope? What does it say?
So question is, what was the magnification on Galileo's telescope and what is it today on modern telescopes?
Fantastic question. I don't actually know. But let me tell you, modern telescopes definitely at least 100 times better, if not 1,000 times better. Yes. 20-meter mirror? So we have never put a 20-meter mirror in space. I believe the largest we put in space is 6 with James Webb. Yeah. Oh, on the ground. Oh, 20 feet, which was 6 meters. Yeah, and on James Webb. Yeah. Yeah, it's just the diameter of the mirror.
So the distance that you can see out into the future, is that proportional to the size of the mirror?
In some respect, yes, right? Because things that are further away are going to be fainter, right? And so you need a larger light collecting bucket or a longer exposure, right? And so if you stare for long enough, right, you're going to collect the same number of photons as if you open up a really big bucket for a really short time, right? Yeah, it's just, that's exactly what it is. It's a camera. Yeah.
So
Yeah,
So what telescope observes light from the earliest universe, and how do we know it's the earliest light from the universe?
okay, so I did not cover the earliest light from the universe. I actually did not put any telescopes that look at the earliest light in the universe on there. There are telescopes like the ACT and Planck that look at what is known as the cosmic microwave background, which is technically the earliest light in the universe. It is everywhere, right? What I did talk about was James Webb, which observes the light from the first stars and galaxies, which is also pretty early. But that's 300 million years after the Big Bang, which is still about 300 million years later than the CMB, or more or less. However, the way that we know what we're looking at is one, it can be the wavelength, right? So as the universe is expanding, right, light gets expanded as well. And so the further that it has to travel to us, right, the more expanded that wavelength will be. It's called being redshifted, literally meaning that it is moving towards the red end of the spectrum. And so light that was UV in the very early universe, coming from the first stars and the first galaxies, is now infrared when it reaches us. The other way to tell is through something called spectroscopy. And so what we do is we look at something and we break down the wavelengths of light, kind of just like I showed you with a prism, right? And in its simplest forms, it's just a prism that breaks up the wavelengths of light. Every element on the periodic table has a unique fingerprint in those wavelengths of light. I didn't bring out the element lamps today. It would have been very, very cool to look at. But if you look at hydrogen, right, it has like 3 or 4 lines in the optical that you can see, and you see very distinct single lines. You don't see a rainbow, right? You'll see a red, you'll see a blue, you'll see a purple, right? I think there's a faint yellow in there. And so every element has its own distinct signature. And so what we do is we look for those signatures and how they are shifted in that spectrum, right? Because again, light that is optical will be shifted into the infrared, right? And further. And so what you can do is you can look for those signatures in different parts of the spectrum. And so lines that we know that exist in the UV, we now look for them in the optical, or sorry, in the infrared with the James Webb Space Telescope. And so that is what tells us exactly how far that light has traveled, right? That redshift is quite exact, right? And so James Webb is finding a lot of things that have redshifts of like 10, right, 13, which means that we are at like a 13th of the size of the universe as it was today, meaning it's very small, right?
Okay, I'm going to do a question from online. What is the fundamental difference between a telescope and a microscope?
I don't know. Maybe somebody else knows who's a biologist and uses a microscope more than I have, like the 2 times in grade school.
It is the configuration of lenses.
There you go.
Yeah.
Amanda knows.
All right, another question from online. If a telescope breaks in space, can you fix it? And
Ooh.
how?
Aha, I love this question. For the most part, no. Many of our telescopes are not in Earth orbit. The James Webb Space Telescope, for example, sits at what's called the L2 Lagrange point. It is 900,000 miles from Earth, in the opposite direction from the sun. So no, not serviceable. But there are some telescopes that are in near Earth orbit. For example, Hubble is in Earth's orbit, and many of you may remember in the 1990s when Hubble first launched, this was a huge catastrophe. It had a problem with its primary mirror. We spent literally millions, billions of dollars to send that telescope up into space, and it didn't work. All of the images were blurry, and so, but because Hubble was close enough to Earth, we were able to send up a mission to fix the Hubble telescope, effectively by putting a pair of glasses on Hubble. So Hubble actually is nearsighted like all of us, and has a pair of glasses. So
Maybe we'll do a couple more from online. Which of the telescopes in the grid were future telescopes?
oh, okay, let's go back. Not that one. We're going to be going forever if we do that. Okay, so I did have this vaguely organized by what was on the ground in space and future telescopes. Rubin, at the time that I made this presentation, was a future telescope. It had first light back in June. And so it's been doing some really cool science, June, July, August, sometime in the summer. It's been doing some really cool science. So Rubin is actually no longer a future telescope. It is active. But HWO, which is the Habitable Worlds Observatory, is really like concepts of a plan right now. Roman is future telescope that will be launched in early 2027, assuming that the government does not pull funding to launch an already finished telescope. So if that makes you upset that we've invested billions of dollars and then we're not going to launch it, you should talk to your representatives. TMT, also a future telescope. TMT very creatively stands for 30-meter telescope.
All right, we'll do one final. What are the current limitations of our modern telescopes?
Oh, so many. The atmosphere, the size, engineering. I could tell you what my ideal telescope would do is it would have infinite resolution on literally everything. We would see all the way back to literally the smallest structures that exist in the universe, all the way out in the early universe. Right now, we can only see those tiny dwarf galaxies around our Milky Way. So infinite resolution in that, infinite resolution in spectroscopy. So we can see all of the chemicals with perfect precision. We have absolutely none of that. So that's my wish list. Anybody who's an engineer, please feel free to work on that.
Okay, let's give another round of applause to Jen.
Thank you.
Okay, we now have some giveaways. So on the back of your seat is a number and a letter. That is how you know. So if I call your name, please shout out loudly so I can hear. Okay, F12. All right, H5, C8,